So early in the formation of our solar system, Jupiter formed and actually started to migrate inwards toward our sun. And when it did this, it basically mopped up a lot of that early protoplanetary debris.
Hmm.
And that's one of the reasons that Mars is actually so small, because Jupiter cleared out a lot of Mars's orbit. Jupiter also cleared out some of Earth's orbit too, which is one of the reasons Earth didn't form into a super Earth, because Jupiter actually came in and started clearing out the inner solar system.
That's crazy.
Yeah. Hello and welcome to Entropy Rising, where we talk about science and futurism. I'm your host, Jacob, and as always, I'm joined with my wonderful co host, Lucas. Lucas, how are you doing today?
Doing wonderful today, Jake. Nice to be back.
Yeah, welcome back. I guess the audience doesn't know, but we took about a 3 week break of recording so you could take a cruise to Alaska.
Yeah, and it was wonderful, beautiful. If you guys haven't been, it's actually breathtaking. So I very much recommend that.
Yeah, I'm glad you had such a good time, and I'm glad you're back and we're recording. Of course, from our audience perspective, there was no lap in episode, so
Yeah, well, it's nice for me to be back.
no, I'm happy you're back. I have missed recording over these past few weeks. Now that you're back, we're going to be talking about the rare Earth hypothesis as a solution for the Fermi paradox. Now, the Fermi paradox, of course, is something we've covered before. We covered it in episode 5, which was an overall episode covering the Fermi paradox, no specific solutions. And then in episode 9, we actually specifically covered the dark forest theory as a solution for the Fermi paradox.
Yeah, which are both like, I love the dark forest theory. It's an awesome theory. It's also just a little bit more on the radical side when you think about solutions to the Fermi paradox. Going over today about the rare earth hypothesis, I think it'll be a little bit cooler because it is much more plausible in my mind that this is something that could be more of a reality.
I think so, yeah. I mean, so the rare Earth hypothesis is more or less a subset of the great filters theory,
Hmm.
which is this idea that from the beginning of life to being a spacefaring civilization that we could actually detect, which would satisfy the Fermi paradox, the question of why don't we see aliens, there are all of these so called filters in the way. And each filter lowers the odds of life making it to the end. So these filters can be lesser filters, which are maybe 50-50 chance or something, minor filters, which could be 10% or less, maybe 1%. And then we get great filters, which is that something maybe a 1 in a million chance. And the idea is all of these filters added together, they compound and make it very rare for life to emerge.
Yeah. And I feel like that is something that's very easy to think about in a way because we all face like these hurdles in life, and life itself faces these hurdles, and we can see it through these massive extinction events that we've had throughout the existence of life on a planet. So you could have millions and millions of planets out there that have microorganisms, but those never evolved to become multicellular just because nothing ever fused. And that's just one example. So I love the great filter theories and all the different subsets of it.
I'm glad you brought that up. The rare Earth hypothesis specifically says that Earth like planets are necessary for complex multicellular life to form,
Hmm.
and that life itself might be very common. You might find microbes under ice capped planets like Europa or, in all these other extreme places, but the rare Earth hypothesis takes it a bit further and says, we're not talking about that. If you want civilization, if you want fancy technology and advanced life forms, you need an Earth like planet. That is a huge supposition of this theory. And we'll definitely be talking about if that's the case later on. But like you were saying, yes, life might be very common. Complex life might not be, according to this theory.
Yeah, absolutely.
So, thinking about, one of the core assumptions of this theory, of course, is that Earth is special and that we need Earth like planets to support life. But is that really the case? Like, why is Earth such a special planet?
Well, when we think about it, right? I mean, we have a very small sample size of what planets can support life,
Yeah.
and it's Earth,
Yeah, that is true.
right? Now there could be, like I was mentioning before, microorganisms living on these distant moons that could be in our neighboring solar systems. We don't know that, right? Because we can't detect any change in that. And then we also think of like tardigrades as just an example, extremophile organisms that can live on asteroids for hundreds, if not thousands of years. So there could be, life out there that we haven't detected, but as of right now, Earth is the only planet that is in a Goldilocks zone that has a temperature that can support carbon-based life and has liquid water, which is the building block of that life,
Yeah.
right? So that those are some of the main core things that make Earth special. Also, it has a magnetosphere that protects it from solar rays. And then we also have Jupiter, which protects us from most life threatening asteroids. So
Yeah.
we really are in a nice protective bubble.
Yeah, that is true. And a lot of those different things, a magnetosphere, which comes with having an active core, plate tectonics, having Jupiter, having our large moon. We don't really know how likely or unlikely these things are. Some of them might be more likely than others. We also don't necessarily know how important many of them are to life. It could be the case that having a Jupiter like planet protecting us from asteroids, you could have life that forms without that. It's just that it's more likely that you have life form with that extra protection.
Yeah.
Could be the same thing with like a large moon. But the real question is given all of these different criteria that life on Earth has, assuming that they're important for life on Earth and how rare they are, you might find out that Earth like planets are maybe one in a trillion. You might only have a planet like Earth that happens once in a galaxy, maybe once in several galaxies, if these different criteria are rare enough.
Yeah. And I mean, really, that's the core of this solution, right? Because having one in a trillion Earths, you still have millions and millions. And as far as we're concerned, infinite possibilities for life still.
It's just that it's gonna be so far spread out that we're not gonna be able to detect it. It's not a question of why can't we detect life if life only crops up once in a handful of galaxies. There could be, like you said, millions, but we're not gonna see life in a galaxy millions of light years away. It's not
That's
something
very
we'd be able to
true.
detect.
Yeah, I mean, we're never going to meet them, so really it doesn't matter as far as what we're perceiving as finding life because, when you think about it as a numbers game, yeah, that life could be out there, but how much does it really matter to us if we're never gonna meet them, see them, or even be able to detect them?
Yeah, absolutely. And there are a lot of these criteria that very unlikely to happen. I mean, just one of them, for example, is that, Earth has a very circular orbit. When we
Mhm.
look at a lot of planets, they're a lot more of an ellipse than Earth is. Earth, I think, has the most circular orbit out of any planet in our solar system.
Well, that'll definitely help as far as, us not freezing to death or burning up.
Yeah. So, Earth exists in this like perfect Goldilocks zone around its star. It has a very circular orbit. And then our own star exists within a Goldilocks zone of the galaxy that it's in. If you're too close to the core of your galaxy, it's much more likely that you're going to get hit by gamma ray burst or
Mhm,
supernova from neighboring stars because those stars are more closely packed.
mhm.
But if you're actually too far away from the core of the galaxy, things like metals become more rare. But I'm talking about metallicity as measured from a star's perspective, which is anything that isn't hydrogen or helium. But these important components you need for complex life, phosphorus, oxygen, they become more and more rare as you move away from the core of the galaxy. So while, yes, we exist in this Goldilocks zone from our own star, it's also likely that we exist in a Goldilocks zone within our entire galaxy.
Which is crazy to think about, and you can even keep expanding it further, like, we exist in a time period of our galaxy where stars and planets aren't colliding as much anymore and causing destructive issues, and then we also exist, if you go out even further, in a good time of when all of space as we know it was formed, and it's less heat and background radiation destroying everything, so it is incredible to think about how I mean, lucky we are to be where we are.
Absolutely. And I mean, it's also worth pointing out our own sun is not a very common type of sun. We orbit a yellow dwarf star, which is actually not a very common type of star. I think it makes up less than 10% of stars in the galaxy, if I'm not mistaken. And we think that our type of star could be very particularly important for life in general. We did an episode on extreme life,
Mhm.
and where we talked about how the most common type of star that exists is a red dwarf star, but they aren't very friendly toward life. I mean, we even talked about it in an episode dedicated to extreme places that you would find life.
Yeah, I mean, it that definitely makes sense just because of the waveform of light that our sun gives off. I mean, it definitely allows for plant life to flourish, which is the base of all ecosystems
Yeah.
of life on our planet. So it really is, when you think about it, an incredible amount of conditions that need to be met just for life to be able to prosper past an infantile state.
Yeah, and we're not even on Earth itself. We're still just talking about our solar system, having the right star, having the right location in around that star and being in the right place in the galaxy. That's before we even talk about some of the other conditions that go along with Earth. You mentioned Jupiter before, and I don't are you familiar with Jupiter's Grand Trek?
No.
It's actually what it's called, the Grand Trek. So early in the formation of our solar system, Jupiter formed and actually started to migrate inwards toward our sun, to the inner solar system. And when it did this, it basically mopped up a lot of that early protoplanetary debris.
Mhm.
And that's one of the reasons that Mars is actually so small, because Jupiter cleared out a lot of Mars's orbit. Jupiter also cleared out some of Earth's orbit too, which is one of the reasons Earth didn't form into a super Earth, because Jupiter actually came in and started clearing out the inner solar system.
That's crazy.
Yeah, and it would have actually continued to migrate inwards and could have potentially became a hot Jupiter and orbited closer to our sun. Unfortunately, had that happened, Earth probably would have never formed. It would have mopped up all of that protoplanetary material, and there wouldn't have been enough left to form rocky planets like Earth. However, when Saturn formed, the gravity from Saturn actually pulled Jupiter back out into the outer solar system where it is now. So that inward migration of Jupiter likely prevented Earth from becoming a super Earth, and then the formation of Saturn pulled it back out into a stable orbit, allowing the Earth to form.
Oh my god. I mean, it's just wild to think about that those can like, anything could have been different in those conditions and just nothing.
Yeah, I mean,
Nobody
if
would be here. Just yeah.
and that's just with Jupiter's track in and out, then shortly after that, we had the famous collision with Theia, which is what caused our moon to form, and our
Right.
moon is such an important component of life. At least some people go so far as to say a moon like ours is a requirement for life on a planet.
I mean, I could definitely say that just when you think about how it affects our tectonic plates. Like for example, and it causes us to actually have a lot of stability on our planet. And then our tides, the ebb and flow of that, being able to read those different signs and using the moon for navigation throughout the planet. But that's way far down the road after life has already formed. But I could definitely see why people put a lot of value on the moon
Yeah.
and attribute it to life being able to prosper on
Oh, yeah.
Earth.
I mean, the collision that caused the moon actually stripped away a lot of Earth's early atmosphere, which may have aided us to have the correct atmosphere we have now. If a lot of those early volatiles had stayed, that could have impeded the formation of our current atmosphere. The impact reliquefied Earth's crust, and it changed the composition of Earth's crust
Mhm.
and actually allowed us to have a thinner, more brittle crust that allows for plate tectonics, which is something else we're going to dive into that people think is another important factor. And then the formation of the moon having such a large moon. I think the moon is the fifth largest moon in our solar system.
Yeah, I mean, she's pretty big.
Yeah, it's really big. It's bigger than Pluto, actually, which is why Pluto was declassified as a planet. Kind of hard to justify a planet that's smaller than your moon.
Yeah, I mean, I know everybody feels bad for Pluto,
I
but
do
it does
too.
not deserve it.
Yeah, no, I do. Once I learned the moon was bigger, it's like, yeah, that's a tough one to sell.
Pluto isn't even circular, really.
No,
It's
yeah,
like it's kind of bumpy. It's like an asteroid.
it's like barely big enough to even like become a sphere.
Yeah, but
But
it'll get its vengeance on us one day.
But having such a large moon relative to our planet size, it helps keep the axis stable and imparts humongous tides relative to any other planet. And considering that tidal pools are one of the places that we think life formed, you can imagine how important tides are.
Oh yeah, the tides are definitely important, and the moon does so much more to influence Earth as far as just it being there. And you wouldn't think so with how small it looks and how far away it is, but it really does have a massive effect on a lot of stuff that has to do with our planet, far before life even formed.
Oh, yeah. And, it's worth pointing out when the moon first formed, it was much closer to the planet. So the effect it had on tides were much greater. So those more intense tides could have helped create bigger and larger tidal pools. And that might have helped life get started even faster than it otherwise would have.
Wow, that's actually crazy. I didn't know that the moon had that much closer to
Oh, a
us when it
lot
first
closer.
formed. How long do you think it'll be before we lose the moon?
I don't know the I don't know the
Before it
number.
just flies off.
Yeah, I know. I don't know the number off the top of my head. I think how far is it moving? It's like an inch or so a year, right? Something like that.
I think it might be like a foot.
Is it? I don't I
Obviously, either of us don't know it, but it does move a little bit.
It does move. Actually, we exist in a very rare time where we can see total solar eclipses. As the moon moves further away, it won't be too long before solar eclipses are impossible.
Oh yeah, because it won't be big enough at our perspective to block out the sun
Yep.
anymore. Oh man, yeah.
So future generations won't have solar eclipses. Don't worry, it'll be millions of years from now, but it will eventually happen.
Yeah, but those generations, they'll get to see Milky Way and Andromeda colliding together before,
That
before
too.
they die in a fiery explosion.
I don't know if we'll still have a moon by then. That might be about the timeline that the moon goes away.
We digress.
You did mention, by the way, plate tectonics, which is something that people think is a huge filter for life.
Yeah, I could definitely see that. Imagine if it was just Pangea all the time, and as the Earth tilted, Like, it just brought all of our landmass to one of the poles. Then without plate tectonics, then, just all the land is frozen. No evolution of, amphibious life that turned into, mammalian and what we are now. We would all just be a bunch of fish.
At least there would still be life.
Yeah.
One of the main reasons people think plate tectonics is so important is because it actually regulates the climate over long periods of time. You get these really long carbon silicate cycles where carbon can be sequestered and locked below our Earth's mantle as these continental plates subside. And that is a way to sequester carbon and creates long term stability in the climate. So if you don't have plate tectonics, if you have a solid, almost cap of just crust, then you don't have any way to sequester carbon. And you can end up with a basically runaway greenhouse effect like what happens in Venus.
I see. Yeah, so you'd essentially be making a rock oven.
Yeah,
Yeah.
yeah. Right now, the models are kind of mixed. There's no way to know how common plate tectonics are. Obviously, we can't observe small rocky planets. A lot of models predict it's incredibly rare. There's actually a variable in the Drake equation for Earth like planets. And under some models, just applying planets that have plate tectonics drop the Drake equation to producing life to almost once a galaxy, if even.
That's incredible.
Just off this one criteria of Earth, which is plate tectonics.
Yeah, I had no idea about that, and I have never valued our Earth's moving plates so much. That's pretty incredible.
A lot of people think it's incredibly important for life. It's still unknown. It could be one of those things that if you don't have it, life and advanced life can still happen. It's just less likely. But it does seem like it's an important thing to have, again, because it creates a stable climate over geological timescales.
Yeah, and I mean, when you think about it, it creates stability, right, by doing that, but it also creates variability in landscapes. It gives us new types of mountains and climates, volcanoes, the formation of new land masses, the separation of continents, which gives us variability in life, and variability in life allows for life to prosper.
Yeah, it's also important too. It releases minerals. We were talking about both in our Water Worlds video and our Rare Life video, not having access to the mantle of the planet means that all of these important minerals and nutrients for life aren't able to be available.
Yeah, I mean that absolutely makes sense because life could form for a little bit, but if there's no way to get those minerals recycled into that ecosystem, it'll die.
Yeah, I mean, we see this even in parts of our ocean that are really deep, deep parts of the Pacific Ocean. They're almost like a desert just because there's just nothing really in the water. Yes, you have sunlight, but you don't have any of these important other minerals and compounds needed for life to form and prosper.
Yeah, and you can also see it in just like small, lakes that are man-made maybe and have tarps on the bottom. If you try to put life into them, it'll live for a little bit, but then it essentially becomes like a toxic cesspool and everything dies.
Yeah,
So
yeah. So it is really important to have access to these things. And so that's why we think plate tectonics could be incredibly important. There is a silver lining. I think some current models of planetary formation suggest that plate tectonics might be more common than was otherwise thought. One of the reasons the old models thought that plate tectonics were really rare is because you need a very, very specific type of planet to have an active plates. Earth actually has a very thin crust relative to its size, and it's very brittle, so it breaks and allows for these tectonic movements. If your planet's larger than Earth, you end up having more material and you have a thicker crust, and because of that, you don't have plate tectonics. You can still have an active core, but you don't have it breaking up into all these different plates and moving around. And if you have a smaller planet, the planet actually cools down too fast. So you end up with a thicker crust that's not able to move around.
see, yeah, that's crazy. So on these smaller or larger planets, is there any other way that they would be able to get those minerals from, like, another source to be able to sustain life, or do you believe that plate tectonics really would be something that's essential to life?
I don't know if it would be essential for life, like, period, but I do think it would be essential for large and varied ecologies that could promote complex life like ourselves. You might have a very simple ecosystem happening without access to huge amounts of resources, but at the end of the day, your food chain is going to be limited by both the energy and the minerals that are accessible. And if either of those are limited, then you're not going to be able to have these complex predator prey relationships that drive intelligence. Because at the end of the day, you don't need a very big brain to eat grass. The reason that cows and pigs have these big brains is to escape predators.
That is true. Yeah. I mean, if there's nothing to push you forward, it's like the same way that you see in, just like relationships with everything. there's no reason to drive forward, then why expend the energy to do so?
Exactly. And even if in the long run they might still get there, it might set back the timeline of life so far that we'll never encounter it. Maybe not having plate tectonics. Who knows? Perhaps intelligent life will find a way, but it might take tens of billions to hundreds of billions of years to form versus on Earth where it happened relatively quickly.
Yeah, and I mean, after hundreds of billions of years, like there's not any planet left to form on,
Well,
usually.
again, these would be having to orbit different stars than our own because our star only has about a 10 billion year lifespan. But there are stars that are between us and red dwarfs that are predicted to last much longer and could potentially support life like this.
Yeah, that's very true.
Not to mention, too, I mentioned on smaller planets, you have the risk that the core of the planet cools too quickly
Right.
to support plate tectonics. But that also means that they won't have the dynamo effect that creates magnetic fields around the planet.
The dynamo effect.
Yeah, that's what causes magnetic fields on Earth, is you have this solid nickel iron core that rotates, and that's what gives us our magnetic fields.
I see.
So, with, for example, Venus, one of the reasons it has weak magnetic fields is that the planet does not rotate very fast at all.
Right.
We think that was another protoplanetary collision that happened that essentially slowed Venus's rotation to almost nothing.
I see. Yeah, I mean, having a magnetosphere, and being able to defend us from these unseen horrors of the galaxy, right? Like solar flares, radiation bombardment is so incredibly important, which is why when we talk about these holes in our ozone layer, it's just a drop in the bucket of the horrors that would come in if our core was not a liquid nickel and iron.
Yeah, it is really important over long-term timescales. I think I mentioned it in our Terraforming Mars episode, what was that, episode 2 now?
That was so long ago.
Uh, so I don't want people to get confused because in that episode, and I've even made threads posts, I said, if you want to terraform Mars, we can forget the magnetosphere. We don't need it. The atmosphere itself provides enough radiation shielding. Earth's atmosphere actually shields us from most of the radiation, even without the magnetosphere. The main concern without having a magnetosphere for Mars or for any planet is atmospheric stripping due to solar wind.
Okay.
Now, I made the claim on terraforming planets that we don't need to worry too much about that because it takes a very long time to happen. If we could put a habitable atmosphere on Mars today, we could live on the surface of Mars in that atmosphere for almost 1,000,000 years before it would be reduced to the point of no longer being able to support life.
I see.
However, 1,000,000 years is not a very long time on planetary formation timescales.
Not at all.
So when you're talking about evolution happening and the formation of advanced life and eventually even civilization, it becomes much more critical to have that magnetosphere then because atmospheric stripping will happen over a course of pretty short period of time relative to how long evolution needs.
Yeah, I mean, when you think about it, 1,000,000 years, that's not even like a fraction of a bit of a period.
Yeah.
When you think of like Jurassic period and just dinosaurs, how long they existed, that's like 1 out of 900 million years.
Yeah, so it's really important over these types of timescales to have a magnetosphere, even if I don't personally think we need to worry about putting a magnetosphere on Mars to protect its atmosphere. These are two very different conditions, if that makes sense. I also want to talk a little bit about water on Earth. Of
Okay.
course, that's a result of us being located in a habitable zone of our star,
Mhm.
but it's important that we remember how that water got here because we did have this early protoplanetary collision with Theia that stripped our atmosphere and would have stripped any water off of Earth. But fortunately, we had this late heavy bombardment, which was just a period of time where Earth was constantly being hit by all these comets and asteroids that brought back a lot of that water and was what we think brought much of the water and maybe even some of the organic compounds that were needed for life to begin.
Yeah, which is another super lucky event
Yeah.
that just allowed for us to have that. But that is pretty crazy to think that all of the water on this planet came from comets and
Yep.
asteroids.
So, of course, it's a lot of speculation and theory, but it is theorized that that is where almost all of our water came from. And it's a widely supported theory.
Well, I could definitely see why, because Earth, when it first formed, was a giant burning, like just
Molten ball of
hellscape.
rock, yes,
Yeah, it
yeah.
was just awful. So when you see depictions of that, it's hard to imagine that there would be water anywhere.
Yeah, there definitely wasn't. And, things like this late heavy bombardment, we have no idea to know how common this is. It could be the case that almost every planet goes through this type of bombardment and it always occurs at a later point in the solar system once things have started to calm down. But it's also very possible that this is a rare event and just we got lucky and there's no way to know. It's so dependent on all of the planets and all their positions on when, where, and if this type of bombardment will happen and
Mhm.
happen to be targeted toward the inner solar system where the rocky planets are. It's going to depend completely on the specifics of each individual solar system.
Yeah, absolutely.
So we might have gotten very, very lucky with that, or, it might be relatively common to see something like that happen.
Yeah, I mean, it's just hard to know because we aren't living in that period right now. So being able to absorb events like that, we could if we look at something that's far away enough, because if it's 900 million light years away, then we could see what was happening 900 million years ago there.
Absolutely. And once we get, better telescopes and a larger data set, we'll be able to refine this rare Earth hypothesis a little bit more and see if this is a more common type of planet or if this is truly a rare planet. And maybe it is, we don't know yet. We just, like you said, we have a sample size of one,
Yeah.
which there's an axiom in statistics that if you have a sample size of one, you should assume that it comes from a mean. You can't really do that on Earth because we have this other statistical bias. It's called the anthropic principle or the observer effect, which is
Mhm.
that even if Earth is a very rare planet, we could only ever find life like ourselves on this planet. So the fact that we're alive and thinking to ask this question could be a bias in the data on its own.
I mean, yeah, that definitely makes sense. It is easier to think about life in a mean and our Earth forming as a mean, but it's just so hard to even grasp like how much life could be out there, but how much there isn't around
Yeah.
us, if that makes sense.
Absolutely. And we still need to go out and explore a lot of our solar system, even and especially our galaxy, before we can definitively say this is rare, this is an uncommon thing, or whatever.
Yeah. And that's what makes the Fermi Paradox so exciting in its own, because there's just so many different things that could tie into life, why we haven't seen it yet?
Yeah, absolutely. I think we've covered a lot on some of the special criteria of Earth that may or may not make it rare. For a lot of these, we don't really know how common they're going to be. We don't know how common large moons are. We don't really know how common plate tectonics are, magnetic fields. We don't have any data for this. And hopefully, as we discover the galaxy, I personally hope we find that Earth like planets are much more common than we might otherwise suspect. But going off this hypothesis, this rare Earth hypothesis, why don't we cover some of the implications if this is true? What if Earth like planets are rare? What does that mean for us as a species as we go out into our broader galaxy?
Well, I mean, first of all, it means that it's going to be difficult for us to find life,
Yeah,
right? Especially with the technology that we have right now and the technology in a foreseeable future. I mean, we found mega Earths out there, but it really just means that although we may not be alone, we may be alone.
I understand what you mean. Yeah, there might be other intelligent space-faring life out there. We just might not ever encounter it.
Yeah, exactly. They might be well dead and gone by the time we even get to a planet that we could see as being life bearing, or they could have already existed or not existed yet, just with how far away they are from us and how far away they always will be.
Absolutely, which is why it's a solution to the Fermi Paradox. If Earth-like planets are so incredibly rare, it's not unsurprising that we don't see anyone around us.
Yeah.
Another thing to think about too is, as we're going out and exploring a galaxy, we've done several episodes now on colonization. But if Earth like planets are rare, that's going to change the game with colonization because it's unlikely we would find a similar planet to our own anywhere near us, especially if it's so rare that there's only maybe one or two in a galaxy.
Yeah, that definitely is something crazy to think about because if it could support life, like our life, then it would probably already have life on it if we're going with the rare earth hypothesis. Because if it has those conditions, it'll have life.
Yeah. So it's likely we would in this case find a lot of planets that are maybe similar to Earth. Like you might find an Earth mass planet that doesn't have a moon, doesn't have a magnetosphere. Maybe it's in too much of a volatile condition within its own solar system, getting hit with asteroids and comets too frequently to support large and complex life.
Yeah.
When we're thinking about how we're going to go and colonize, it's unlikely we would be colonizing planets, I think, at that point. Or if we did, it would be at the point we could terraform them.
Yeah, I mean, we've talked about it before. Like planets are overrated.
Yeah, I mean, that is true.
But just hypothetically, if we did want to go out and colonize planets, it could be the same thing like how you were talking about with Mars. Maybe it isn't suitable for forming complex life, but complex life, if it were to go there, could thrive.
That is true. It's so expensive and energy intensive to launch an interstellar colony ship. Even in my mind, I think the only reason you would do it is if you had an ideal target already picked out. It just kind of seems a bit of a stretch, at least in the early days of interstellar colonization, that you would fund such a mission to go to a place that had nothing but dead, cold rocks that still needed to be terraformed for hundreds, maybe even thousands of generations. at that point, it's hard to justify, I think, leaving our solar system.
It definitely doesn't make sense, but we've had a viewer mention before that we didn't mention in our colonization episode that we would probably send out scouting probes first, right, to go and look at these planets before we sent out colony ships. But really, all of this is super hypothetical because just leading back, it would just be easier to build an O'Neill cylinder and just hang out around the sun in that solar system because ours is too crowded.
Yeah, but I have a hard time imagining a situation where our solar system is too crowded for another O'Neill cylinder. I mean, it is possible you could get to that point of using up all of the material in your solar system, but that is very, very far in the future. I mean, at that point, you might even be getting toward the end of the lifespan of the sun. Although that could be a solution to why we would go and explore the galaxy, even in the event that there's nothing but dead, cold rocks out there, is because our sun does have a limit on how long it'll live. Granted, we can live around our sun in O'Neill cylinders much, much longer than we could live on Earth, because, O'Neill cylinders can be moved away and they can, as the sun expands and enters its red giant phase, you can just adjust the orbits of your O'Neill cylinders to compensate. But still, eventually, our sun will die and we will need to move on. So perhaps even in a rare Earth hypothesis situation where planets like our own don't really exist in our galaxy, we would still find ourselves colonizing the galaxy by force, just maybe at a much later time.
Yeah, and at a much slower pace than many would think,
I would
right?
think so.
Because I mean, we could essentially become like nomadic, following high efficiency and sustainable stars.
I could see that for sure. Yeah, move and settle. And I feel like once you launch that first interstellar trip and you lose your home planet, justifying going to the next star makes more sense. And maybe we could be nomadic and we could go from star to star, slowly colonizing while trying to find that hidden gem, another Earth.
Yeah, but you bring up a good point there that once we leave our home system, what's stopping people from just branching off and going and forming, if for nothing else, in the spirit of adventure and exploration, something that has driven humans for all of existence? We just want to go and find stuff first.
That is true. And, I think maybe that could even happen in this situation because you might try to find another Earth or another habitable planet.
Yeah.
And I feel like you would end up with different sects of people, maybe some that are trying to find a close enough planet and terraform it. And maybe others who say, that's not it. We know one Earth existed. We'll find the other one. And they're just dedicated to going from star to star to star and trying to find truly another Earth.
Yeah, and I mean, it could just like be driven by religious sects. Just we have no idea what could drive people to want to do that. But at the end of the day, if we are looking for another planet, we would want something that is similar to Earth.
Absolutely. And I think especially in the non-negotiables like mass, because it's much harder to change the gravity on a planet than it is to change the atmosphere. So finding a planet with the right mass and especially maybe even the right mass with a magnetic field or the right mass with a large moon to keep it stable.
Yeah, I mean, I could definitely see like a little bit of deviation. You just have like shorter, thicker humans starting to form with bigger bones.
Well, it's also, if you've got the technology for interstellar travel, you can fix a lot of issues with a planet. I do think mass would be one of the most expensive things to fix, but even that's easy enough to fix. Redirect some asteroids or maybe even redirect a smaller planet and create almost like the same collision that formed our moon.
Yeah, I mean, might as well. If we're at the point to where we're just hopping willy nilly
Yeah.
between solar systems, then we probably have the technology to where we could bend gravity and space time and just collide large masses.
Or just, slap big rockets on them or do a gravity tractor. There's a lot of different options
Oh,
to do
yeah,
it. Redirect
absolutely.
orbits. Maybe find another smaller planet and just put it in orbit of your Earth like planet. Lots of options.
Those people are so lucky living that time when the crash moons together. Sounds.
I hope so. Maybe we'll get radical life extension. Who knows? I do also want to talk about Independence Day, right? The whole notion of that
Oh,
was that the aliens were invading because Earth like planets were incredibly rare and we were mistreating ours. If I'm not mistaken, I think that was
yeah,
the plot
no,
of the movie.
and they wanted it.
Yes. So I do wonder if that is a more possible situation in a rare Earth scenario. I personally don't think it makes much sense to invade a planet just because there's so many resources out in space and they're not locked behind a gravity well. But if Earth like planets are actually necessary for life, if life can't exist on any other type of planet, again, questionable. But if that's true, and if it just so happens that there maybe happen a handful of times in a galaxy. Maybe you have 3, 5, 10 Earth-like planets in a galaxy.
Hmm.
Maybe they're highly coveted, and if you do have a space empire, they might not think twice about knocking off the natives and taking the new planet.
Yeah, I mean, it could be like you were saying, a valuable resource, and it could be that for many reasons. So they're like, well, we need more room. These guys don't even have like interstellar travel yet, so let's just won't get rid of them. That's a nice little rock for us.
Yeah, exactly. I'm not necessarily convinced this is a probable outcome, that rare Earth hypothesis leads to alien invasion, but I guess I can kind of follow that logic a little bit, and I might be willing to concede maybe in this circumstance it makes a little bit more sense. Although I still think just to do interstellar travel and then take over and colonize a planet with inhabitants, at what point is it easier to terraform a closer planet? So that's my only like balance between saying that's not exactly likely.
Yeah, no, I mean, it definitely isn't likely. There would have to be something out there that we just cannot grasp yet that makes Earth-like planets incredibly rare. Like they may want it for research purposes,
Yeah.
like being able to run simulations of life on, or maybe they just want to scan it. We don't know, but it is a possibility. It's just very slim.
I think so too. I will say this on the bright side. You said the rare earth hypothesis ties into the great filters, which is the rare earth could be one of the great filters. Maybe it is one of these one in a million filters that prevents life from being big. But if the rare earth hypothesis is true, that tends to lean toward the idea that we've actually already passed all of the great filters.
That is actually exciting to think about because, it definitely could be. Like, life has been around for, in our perspective, a really long time, and we have gone through a lot of stuff that should have wiped life out completely, but it didn't. So it is definitely possible to think that we have surpassed a lot of those filters, and we've kind of made it just to this point to where there aren't a lot of people who have.
Yeah, and that could mean that, the reason there aren't a lot of interstellar civilizations is just because there's a lot of early filters and we've cleared those and we're one of the only life forms in our galaxy that has. And that could give us a nice bright future.
Yeah, well, everybody give yourselves a pat on the back.
Yeah,
I
you
mean,
did it, guys.
yeah, we
Congrats.
made it. Congratulations.
That being said, though, we've had this entire discussion based on a couple of assumptions. There are some very important assumptions with the rare Earth hypothesis. One of them is that you need an Earth-like planet to support life, which I think I mentioned in the intro we were going to talk about because I
Mhm.
don't necessarily think that's true.
Okay. So what are you thinking? Like, I mean, I know that we've gone over it, but non-Earth like planets, like how extreme from Earth do you think those planets could be and still support life?
Yeah, so we obviously only have a sample size of one, and it's not surprising that we're looking at ourselves and we're thinking, "Wow, all of these things are really important to support life, and it's crazy that we have them." But life is very adaptable, so it's very possible that some things that we think are critical, like maybe a large moon, life could happen without that anyways. It's just that it's maybe less likely, or maybe it's not less likely. We don't know. There's also just different types of life, right? This setup works great for carbon-based life as far as we can tell, but we could potentially see different biochemistries. There's this wide notion of silicon-based life. We've even mentioned using different solvents, talking about methane-based life, and then
Mhm.
there's even ammonia-based life. So there's all kinds of different biochemistries that could happen that might not be very suited for an Earth-like planet. They actually might find this to be a very inhospitable planet.
Yeah. And that's definitely possible. But with every factor that we put in where life could exist without an Earth like planet, makes it more and more confusing why we don't see any around us.
That is true. I also want to point out you could potentially have different setups even for life like us. If you can imagine a Earth-like planet that orbits a gas giant like Jupiter,
Okay.
now you might not need a large moon. You might not even need a magnetosphere because you can be protected by the magnetosphere of the gas giant, especially if it's closer to the inner solar system, a little closer than Jupiter is. You could have a moon orbiting a gas giant that's in the habitable zone of their star. And this could completely change the criteria needed for an Earth-like planet.
Yeah. I mean, it would switch up like different day and night cycles and how all of that works. I mean, it would definitely produce unique life.
It would, and it gets rid of some of these things that we thought were required. Many people point out and say you have to have a magnetic field, but here's a planet that doesn't have one that's protected by the magnetic field of its gas giant.
Yeah, that is actually a very unique thought because you could have a solid core planet that still has the longevity to survive for hundreds of millions of years and produce complex life. Yeah, very cool.
So there are definitely, I think, different setups that can support life, even life like our own, that aren't necessarily Earth-like. I think it's going to be almost like a local minima, where if you plot all of the different criteria that can go into a planet, you're going to find just local minima where everything comes together to form a planet that can support life. If you drift away from that local minima, the odds of supporting life drop to almost zero until you stumble across another combination that can support life. So you might have all these different criteria that can support life, but you still need the right set of them, if that makes sense.
Yeah. I mean, that's thinking of life as almost more of like a path of least resistance for how energy directs itself, which if that is the case, I'm rooting for it because as we progress with being able to observe the universe, we might see a much higher abundance of life if it doesn't just need a rocky planet
Yeah.
like Earth.
Yeah, absolutely. So that's one of my biggest issues with this theory is that I question that core assumption that you need an Earth-like planet in the first place.
But then now, assuming that we don't need an Earth-like planet, then we should be detecting more life out there.
Well, that's the broader Fermi paradox, isn't it?
I mean, it absolutely is, but it's like why like we have different ways that we could be detecting life. A lot of people they talk about building Dyson spheres or Dyson swarms around planets. We should be able to see that flickering. It's just in our observable universe, if we didn't need an Earth-like planet and there were other ways for life to be supported, I feel like we would have seen just like something.
Yeah. Well, see our episode on the Fermi paradox.
I
Yeah, no, I agree. And I personally lean toward the great filters theory, which I guess the rare earth hypothesis is a subset of. I do think that habitable planets is a filter, maybe even a great filter. I just don't necessarily think it's as great as the rare earth hypothesis says that it is.
Okay.
I think there are different combinations and criteria needed to support life that will also work. I don't think you need exactly what we have here.
Yeah.
And
I can definitely get behind you on that.
and I also just think that life and even intelligent life is a little more adaptable than I think some of the proponents of the rare earth hypothesis seem to give it credit for.
Well, when we start getting into intelligent life, especially life that is more intelligent than we are now, that adaptability is probably exponential.
It's just getting up into the point of because you need a good period of time of stability. And I do think stability is very important.
Yeah, it definitely is. But we could have civilizations out there that it only took 50 million years
Yeah.
to get to a intelligent point that's close to ours,
That is
or
true.
even succeeds ours. Just because they got more lucky in that evolutionary scale, they were able to adapt and create a better nutrient system to build bigger brains.
I
It's
always
just ours happened to take a really long time.
One of my favorite thought experiments is like, what would have happened if humans had developed when the dinosaurs had? There's no reason we couldn't have. We had all the right complexity and everything was there, but it would have been a very interesting case. There's no reason we couldn't have seen intelligence like ours form much earlier in the planet's history.
Yeah, thinking about that, right? Like we were hunted pretty brutally for a really long time.
We were not on the top of the food chain.
No, God, no. So we probably would have been snacked on, but we would have eventually made it. And I feel like we would have made it through the asteroid and maybe progressed a little bit better because there would have been a lot of charred dinosaur meat to enjoy afterwards.
I don't think there's any reason we couldn't have had humans form 65 million years ago instead of dinosaurs. If we had our level of technology 65 million years ago, we could have colonized the entire galaxy multiple times over by now.
Oh yeah, yeah, and that's definitely what I'm saying is like, and what you're saying too is that just life could move and it moves in erratic ways, and that way could be the intelligence that we have now at any point in time.
Well, is there anything else you have on the rare earth hypothesis?
No, no, it's been a super interesting topic to talk about.
I think so too. I always do love the Fermi paradox. This is not the first time we've talked about it, and this will not be the last. There's several different. Oh God, we're gonna revisiting this. I think the entire time we have this podcast.
Yeah, which we should because it's just one of the most exciting things. Like where's the life,
Yeah.
right? We talk about UFOs and crazy sightings. It's just so much fun to dive deeper into it and just really think about why we haven't seen anything, and maybe we have and we just don't know it yet.
Well, thank you all for joining us on this episode. If you enjoy the episode, consider liking or subscribing on whatever platform you're on. We also have a Patreon if you feel so kind as to support us there. Totally understand if you don't, but we always appreciate it. Next episode, we will be revisiting interstellar colonization. We've already done 2 episodes on the topic, how we would build the ships and what life would be like on an interstellar colony ship. Next episode, we'll be talking about what we'll actually do when we reach our new interstellar destination. So if that sounds interesting, please join us for that discussion.
Yeah. Thank you all so much for your never ending support and following us through this whole journey, and look forward to seeing you next week.
Take care.